Good day, sir. I'm Carlos Isibano from BCMA. From now on, I'm going to discuss about the real gases and its characteristics. So, what is real gases? According to the definition, a real gas is defined as a gas that does not obey gas laws at all standard pressure and temperature conditions. When the gas becomes massive and voluminous, it deviates from its ideal behavior. Real gases have velocity, volume, mass. When they are cooled to their boiling point, they liquefy. In another hand, real gases defines are non-ideal gases whose molecules occupy space and have interactions. Consequently, they do not adhere to the ideal gas. A real gas is a gas that does not behave as an ideal gas due to interaction between gas molecules. Any gas that exists is a real gas. Real gases have small attractive and repulsive forces between particles and ideal gases do not. Real gas particles have a volume and ideal gas particles do not. So the question here is, which are the real gases? Any gas that exists is a real gas, like oxygen, hydrogen, carbon dioxide, helium, carbon monoxide, and etc. Real gases between particles have small attractive and repulsive forces, and ideal gases do not. There is a volume of true gas particles and ideal gas particles do not. To understand the behavior of real gases, the following must be taken into account. First, compressibility effects. Second, variable specific heat capacity. Third, van der Waals forces. 4. Non-equilibrium thermodynamics effects. 5. Issues with molecular dissociation and elementary reaction with variable composition. For most applications, such a detailed analysis is unnecessary, and the ideal gas approximation can be used with reasonable accuracy. On the other hand, real gas models have to be used near the condensation point of gases, near critical points, at very high pressure to explain the Thomson effect, and in other less usual cases, the deviation from ideality can be described by the compressibility factor Z. Real gases originate from two factors. First, the theory assumes that as the pressure increases, the volume of a gas becomes very small and approaches zero. While it does approach a small number, it will not be zero because molecules do occupy space and cannot be compressed. Second, intermolecular forces do exist in gases. This becomes increasingly important in low temperatures when translational molecular motion slow down almost to a halt. However, at high temperatures or even normal everyday temperatures, the intermolecular forces are very small and tend to be considered negligible. So here we have an example of plot to help us understand the behavior or characteristic of real gas at different temperatures. And the gas that is used here is nitrogen or N2. Starting first at temperature 200 Kelvin, this is how the core will look like. As we seen here, the color green at 200 Kelvin is too far from the ideal gas. So, and if we hit this farther to 500 Kelvin, the curve will look like this. At 500 Kelvin, observe that the curve color red seems to be getting closer to the ideal gas. So we have noticed that when the temperature is increasing, it is getting closer to the ideal gas. From this, we can see that as the temperatures goes higher, the curve also get closer, especially at the low pressure region. Automatically, temperature decreasing, it departs from ideal gas. So what I have said earlier, the more the temperature increase, it getting closer to ideal gas. So that exactly what's going on here. The 1000 Kelvin temperature colored blue curve is a lot closer on the ideal gas, and this suggests that real gas behaves closely to ideal behavior at low pressures and high temperatures. A real gas behave closely to ideal behavior when the low pressure and high temperatures. For a gas at low pressure, large volume, the volume of the container is very large compared with the volumes of the particles. Thus, at high temperatures, the particles are moving very fast that the effect of interparticles interactions are not very important. Also, the particles are moving at a constant motion, which we will get the gas to behave similarly to an ideal gas. Real gases. In real gas, there are some attractions among the particles, thus the particles will hit the walls of the container very slightly or less often. And to illustrate this, we have here an example on how this particle behaves. So we can see the pictures, the next. So we have here a particle, and as you can see, the white particles in the center surrounded by colored black particles is traveling outwards, indicated by an arrow. And as shown, the interactions on the inner particles will cancel each other, and the interactions therefore are least effective. However, if we look at the interactions on the particles closer to the container wall, we see that the interactions of the particles in front of the container wall are more effective, and therefore the particles will pull to the inside of the gas and hitting the container wall less often or with less force. This will then affect the pressure. Here we have the real gas equation, also known as the van der Waals equation. So the formula is P observed plus A open parenthesis N over V close parenthesis raised to 2 times open parenthesis V minus NB close parenthesis equals to nRT. Now, at low pressure and the high volume, the pressure of the gas is greater than the observed pressure of the real gas, and the volume of the ideal gas will be less than the volume of the real gas. At low pressure and high volume, ideal gas pressure, or P ideal, is greater than pressure observed. So the relationship of ideal gas and real gas is P equals to P observed plus A N over V raised to 2. In ideal gas, volume or volume ideal is less than real gas in volume VR. So the relationship is V ideal equals to VR minus NV. That is all, and thank you.